Welcome to Calculus. Fractions will pop up when you least expect it. On this episode, Stevenson will demonstrate
the second part of the fundamental theorem of calculus shows us how we can actually calculate or evaluate definite integrals using the antiderivative. So we've kind of seen this a little bit before in the previous lesson, but this is the second element or consequence of the fundamental theorem of calculus. So if you know your function is continuous on a closed interval, and if your capital F is an antiderivative also on that closed interval, then the integral from a to b of f of x dx is just the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. Okay, so this rule basically, or this relationship is super important. It basically tells you that any continuous function can be figured out. This definite integral of any continuous function can be calculated without any limits. No Riemann sums, and usually pretty simply, especially now that we have technology, right? As long as an antiderivative can be found, this will hold true. Let's go ahead and now try to actually implement this fundamental theorem. So off to the right, I have your fundamental theorem in terms of evaluation right here. And then there's two sets of notation we can use to evaluate our antiderivative at its upper and lower bounds. Makes it a little bit more cleaner, your work, a little more compact. So first thing we need to identify, what is my derivative, right? What is my inside? What's my integrand right here? So remember, that represents the integrand, that's your f prime, right? So remember, with this integral, with this fundamental theorem, remember little f represents the derivative of capital F, okay? So where does little f in this case come from? Well, we have to do reverse power rule. So add 1 to the power, so it becomes 4. Divide 4 into the coefficient, which in this case is 1, so we have 1/4, plus. Now, where would 1 come from? That's a constant, which means it must come from a linear function f. So x. So this is my antiderivative. So now I'm going to rewrite this using this notation here. This integral, because of the fundamental theorem of calculus, is really this antiderivative evaluated from -1 to 3. Here is my answer. I have my antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So what I'm going to do now is follow order of operations and simplify this.